Hello everyone, today I'll talk about the solution to the problem myCalendar1. This is a very standard data structure problem. Since we want to maintain a set of non-intersecting half-open intervals, and when we want to add an interval to our set, we can only do that if the resulting set would also be non-intersecting. And this is the only thing that we have to implement, that addition of a new interval. So it would be natural, and this is the key insight to solving this problem, that let's say that we have a timeline here, that we look at our intervals in the sorted order. That's very natural whenever you have a timeline. So these are left ends and right ends. Right ends are open. And non-intersection, of course, means that at any position there is an interval. And of course, we could have a situation where there is an interval immediately touching another interval. That's allowed. And so now, if we want to add another interval, it might be non-intersecting, or it might be intersecting. There are many ways for it to be intersecting. And we have to come up with a short condition that we need to check to see if our interval is indeed okay to fit without intersections. And probably what we're going to need is to find the intervals that are close to it. So maybe those intervals close to it in our sorted order. And since after adding this interval, so for instance after adding this interval, the whole list changes, we cannot simply use a sorted list as in a list that is in sorted order, because for instance by pushing this interval here, we would have to move all the other elements forward or all the previous elements backwards, but still it would have linear time, and so in a pretty easy to construct pessimistic example, our solution would be too slow. And the standard way of representing a sorted array with modifications allowed is a binary search tree, which unfortunately Python just doesn't provide anywhere in its standard library. It's possible to use something called sorted list from sorted container, the sorted containers library, and you can do it on LeetCode. However, on other platforms, in particular I think on Codeforces, sorted containers are not available, and you should use your own implementation of BST. But I'm getting ahead of myself here. So the first thing that we really need to do is to motivate the use of BST by coming up with the exact condition that all the new intervals should satisfy for us to be able to add that interval into the set. And the condition that I propose, though there are other solutions, is when we have an interval, if it intersects with some other interval, then since the intervals are non-intersecting otherwise, it should intersect with the interval that starts before this new interval ends and is the closest, when it comes to starting, to this interval's end. So in other words, when we have this open in parentheses, we find this, or close in parentheses, sorry, we try to find this open in parentheses, this inclusive parentheses, that's to the left of our open one, but as close to it as possible. So essentially the previous interval in that sense. And if that previous interval ends before the new interval starts, such as in this case, this interval ends here, this interval starts here, that's fine. They are non-intersecting. Otherwise, and of course it can end exactly at this position, this is by definition. And for instance here we have a bad interval, so we look at the first interval that starts before this new interval ends, this is this green interval, and we see that it ends after our new would start, so we cannot add it. This is a straight up intersection. And also it works whenever, for instance, our new interval is wholly included in another interval. The first interval starting before our end is this one, and it doesn't end before our start, it actually ends after our start. If we were to include some larger interval, because we have to think of all the edge cases, then the first interval that starts before our end is exactly this one. And it also ends after our start, so it's bad. So we have to be able to find the previous interval that starts before some value. We'll be holding pairs, but it's not really necessary to do anything special about it. Pairs are just compared first the first value, then the second value. So let's jump to the implementation. And as I mentioned, you could use sorted list. It would be very similar to our current solution, and for the sake of people who cannot use sorted containers because they like practicing on code forces, for instance, you should use your own implementation of BST or use a publicly available implementation. One publicly available implementation of one binary search tree is the implementation of a tree in the PyRival competitive programming library. Here you have a link to the GitHub, or you can just search PyRival. We'll be using a tree set. So this is a BST built on a tree, which is a binary search tree on values with random priorities, and those random priorities are used to maintain heap ordering on them. If you're not familiar with a tree, then feel free to read up on it. It's a very interesting topic. But this will be our binary search tree. This binary search tree will give us standard lower upper bound. In this case, there is the floor method, which will find something that's as big as possible but smaller than the pair end 0. So anything with start that's smaller than end, but the thing that's most to the right, that's the biggest. So this will be the previous interval. If that previous interval doesn't exist, then we're happy. Or so, if it exists, then we have to check something else. If it wouldn't exist, we would be happy. And if it exists, then we look at when it ends. If it ends after our new interval would start, then we have a contradiction, we have an intersection, we return false, we don't do anything. Otherwise, we add our new interval to the set, we return true, and this is the whole solution.